Hey guys, Mr. Betts here. I want to continue talking about different methods that we're going to use for finding antiderivatives. So up to this point, essentially what we are doing is if we have an integrand that we want to take the antiderivative of, it has to be something that is the derivative of something that we know. Now we want to look at more processes that we can use that we can kind of analytically evaluate antiderivatives. So keep in mind that our differentiation rules are going to provide the foundation for finding antiderivatives. So most of the differentiation rules that we have, we're going to reverse in some way. So in order to reverse the chain rule, we're going to use something called substitution. And substitution is exactly what it sounds like. You've done algebraic substitution many times in the past, but we're going to look at how that applies to finding antiderivatives. So quick refresher on the chain rule. If we have a composite function, so a function of a function like f of g of x, or the specific example here, sine of x squared, we take the derivative of the outer function, we keep the inner function inside, and then we multiply by the derivative of the inner function. So if you think about how we would reverse this, this is the derivative of this. And so if we're taking an antiderivative, if we have something like that where we have a function within a function and its derivative is in the expression, then we can reverse the chain rule. So the process that we're going to use is going to use the chain rule here, but we're going to flip it around. So a basic example based on the derivative that we just found, if the derivative of sine of x squared is this, then the antiderivative of that is going to be sine of x squared. We just need to come up with a process to be able to do that. Also, don't forget with antiderivatives that we need that constant of integration. Unless we're evaluating a definite integral with the antiderivative, then that's not necessary. So this is kind of a formula, but we're not really going to use that formula that gives us a process for that. But the idea is that if we have a composite function in our integrand and the derivative of the inner function is in our integrand also, and it's a factor, then we can evaluate the antiderivative using what's called substitution. Before I get into the process of substitution, I want to talk about a way that we're going to take derivatives. Normally with a function like u equals sine of x, if we're going to take the derivative, we would say du dx. So the derivative of u with respect to x is going to be cosine of x. For the purpose of substitution, keep in mind that our integrals are going to be the integral of something with respect to x or with respect to u. And the idea here is we're going to be changing this differential. And so we're going to need a relationship between the differential that is in the problem and some other differential when we integrate. So what we're going to do is essentially take this equation right here and solve for du. So we get, if we multiply by dx, we get an equation that looks like this. This is kind of a version of implicit differentiation. So if you think about if we were doing implicit differentiation and taking the derivative, say, with respect to t, just some variable that's not in this equation, we would get du dt is equal to sine of x dx dt. And so in this equation, we have the du here that relates to the du here and the dx here that relates to the dx here. We also have the dt's in there. So what we're doing is we're kind of taking the derivative using implicit differentiation without that third variable. So we're just using the differentials by themselves. I do want you to keep in mind that the differential by itself is just a value that is going to zero. So by itself, it doesn't mean much. So an equation with a differential in it does have to have another differential in it to get a relationship that we can interpret as a derivative. So anyway, long story short there, when we have equations like this, we're just going to jump straight to that. So for example, here, when we have u equals sine of x, we take the derivative of the left side and get du. We take the derivative of the right side and get cosine of x, but since that's with respect to x, we multiply by dx. So this is just a shortcut from the way we were taking derivatives before, and it's going to allow us to use substitution more easily. So here's the process for evaluating antiderivatives using substitution, and particularly for indefinite integrals. I will briefly go through how we're going to do this a little bit differently with definite integrals in another video. So first thing we want to do is choose u. And the idea here is we want to simplify the expression by choosing u. And we also are going to be taking the derivative of u in order to get rid of the dx. So we want to keep that in mind also. Okay, early on, you may not really understand where the u is coming from, but I think with some practice, it'll become a lot easier. So I'm going to choose u to be this inner function here. So thinking about this being the reverse of the chain rule, that looks like an inner function. So I'm going to let u equal the sine of x. And then what we're going to do is we're going to differentiate u. So we're looking for du equals something in terms of x dx. So this is what I was talking about on the last slide. We're just going to take the derivative of u and get du. Keep in mind that differential is just a number approaching 0. And then on the right side, we take the derivative of sine of x and get cosine of x times dx. All right, so this is the new way that we're taking derivatives for the purpose of substitution. And now we want to substitute. So the idea here with the substitution step is we want to replace all of the original variables. So all of the x's need to become u's in this problem. So the sine of x part is really easy. That's just going to become u. To replace the dx, which also has to be replaced because I have to get rid of all x's, what I'm going to do in this equation right here is solve for dx. So dx is equal to du over cosine of x, and I'm going to replace the dx with that. Now, I do know that there's a cosine of x here, and we'll deal with that in a minute. But right now I'm focused on the u substitution and the dx substitution. And so we get the antiderivative of cosine of x times u to the third power times dx is going to be du over cosine of x. Now, here's where what I was talking about in step 1 comes into play. If we've chosen appropriately, what's going to happen at this point is all the x's that remain are going to go away. So the cosine of x here and the cosine of x here cancel each other out. And now we just have the antiderivative of u cubed with respect to u. Okay, so I have no more x's in my problem, in my expression. Now I need to evaluate this antiderivative just in terms of u. And I've gotten an expression now that I can just use the power rule. Now remember, we're doing antiderivatives, so the reverse power rule, to evaluate this. So I increase the power by 1, I divide by the new power, and then when I take the antiderivative, we need to make sure that we have our constant of integration. So as soon as we take that antiderivative, as soon as this integral symbol goes away, the plus c comes into my answer. Now the last thing is, we just made up this variable u for this problem, so we need to write our answer back in terms of the variable in the problem, which is x. So I'm going to take this definition that we made for u at the beginning, and I'm going to make that substitution again. So where I see the u, I'm going to put sine of x in there. So we're going to have sine to the 4th of x over 4 plus c, and that's going to be our answer. Now, with any problem like this, when we take an antiderivative, we can check our answer by taking the derivative. And indeed, if we take the derivative of this using the chain rule, we would get what we started with here in our integrand.